Welcome to Module 1 of this short course. We'll be giving a number of examples of the use of the MIT Mathlets in various teaching situations. Several of these examples come from a presentation in July 2013 at a workshop at MIT attended by high school teachers from around the world. Our first example is an introductory lecture addressed to a general audience of science teachers. What I hope you get out of this video is that it's possible to give a pretty traditional lecture based on a Mathlet. What I hoped the audience got out of this presentation was, well, the same thing. I was also trying to support the contention that mathematics is a highly visual and intuitive subject. In using a Mathlet in lecture, it's important to realize that the students are much less aware than you are of the manipulations you perform. I tend to announce what I'm doing when I grab a slider or push a button. The students can't see that maneuver. All they can see is the effect. Also, many of the Mathlets carry a lot of information. Students don't comprehend it all at once. In fact, at first they understand nothing of what's on the screen. You have to lead your audience through the various visual components with care. Watch how I do this in the following video and see if I pace it right for you. So I'm going to begin by modeling how I might use some of these applets in a lecture. And I'm going to go clear down to the bottom here and go to Phase Portraits Cursor Entry. This is a nice picture. For the cognoscenti, this models a homogeneous linear system of differential equations. This whole thing is controlled by a matrix, and you can see the matrix down at the bottom here. I've called it A, and it has these particular values right now. A matrix, a 2x2 matrix, determines a couple of numbers. You can take the sum of the diagonal entries, that's called the trace, and it also has a number called the determinant. And those two numbers determine most of the pattern that you see here. They control the dominant features of this pattern. By changing the trace and determinant, I will change the way the pattern looks, and you'll see that. I can adjust the matrix by moving its trace, and you can see what happens. The pattern of trajectories changes when I do that. Or I can change the determinant using this slider over here, and that also changes the pattern of trajectories. In fact, I can change both the trace and the determinant together with a single control in the middle here. So this little plus sign in the trace determinant box is alive, and I can move through this trace determinant space by just pulling that cursor around, and you get quite an active display of the different trajectories that occur. So far I've just been inside of this little part of the parabola. Now I'm going to start to explore more widely and push over across this vertical line. So here the spirals get tighter and tighter and tighter and tighter until when you hit that vertical line they become circles. These are periodic orbits in the parlance. If I continue to move over, the trace is negative. I have a stable system, as they say. Now the trajectories are running in. You can see the little arrows on the trajectories. They're running in towards the origin. They're moving around here. Now I'm going to come down here towards the green section. You'll notice that the trajectories are all yellow. I'm in the yellow section of the parabola right now. If I push down through here, there's this marginal case that happens. It's red, and then that's followed by another completely different pattern of trajectories. This is called a node, and again it has different shapes. And if I continue to push down here, I get another marginal case, a sort of comb figure, and then down here these are called saddles, and there's a great variety of different saddles that I can see by wandering around randomly in that blue area. And so then I can complete my tour by going back through the unstable nodes and back to unstable spirals, which is where we began. So the student can see. Now a student can solve these things. The student can solve these equations. They solve these equations by finding eigenvectors, and there's a complicated procedure that you do with a piece of paper and pencil or with MATLAB. And when you do it, you find that different kinds of functions get involved in the solutions. For example, these spirals involve sines and cosines. These nodes down here do not. They just involve exponentials, and the saddles just involve exponentials. And so students are prone to think that these are completely different situations with no relationship to each other. But one of the things this tool does is to let you see the smooth morphing that goes on as you move from one section to another. There's no jumps. It's a smooth motion. They're all continuously connected to each other. And that's part of the lesson. So there are a lot of lessons here that are extremely difficult to convey with chalk or talk in a lecture situation. And you can imagine sending students home to conduct various exercises with something like this. I chose to begin with this applet because it's visually dramatic. I thought it would be a good introduction to the applets for a general audience, despite being mathematically quite advanced. It's also a great example of a Mathlet which illuminates some piece of mathematics far better than any static mechanism could do. Here are some things I'd like you to think about arising from this little lecture fragment. First, when you first saw the Mathlet, there was a lot of information on the screen. Do you remember how you felt? Were you confused by it? I ask this because your student's experience will be not too different from your own, unless you've seen an applet like this before. Second, I introduced the various windows and functionalities of the Mathlet over a period of several minutes. Make an ordered list of these in sequence and think about other ways I might have presented them to this audience. Third, there are still other aspects of this tool which I didn't talk about at all. Suggest some additional investigations one can pursue using it. This is a good time to point out some of the common features of the MIT Mathlets. Briefly, all the MIT Mathlets exhibit a high degree of interactivity, narrow focus, multiple linked representation of information, click and drag control rather than keyboard, and a uniformity of style and convention. Finally, let's ask, what are the advantages of the use of this technology that were brought out by this example? I think you can distinguish several different ones. First, the visual cortex occupies a large amount of real estate in the human brain. Visualization is a great way to convey information. Moreover, many parts of mathematics have a large geometric or visual component. Linear phase portraits provides a great example of this. Second, in teaching mathematics, one often has to cope with a tension between the general and the particular. Students understand general statements through particular cases. In fact, we all do that. But if you write down a special case, it's not necessarily evident what aspects of it generalize and what are accidental. The Mathlets allow you, or better, the student, to explore a whole continuous range of special cases. Together, they convey a much better picture of the general case than any small number of special cases can. Now, on to the next segment. The second segment of this module models a more interactive lecture style. Because my audience was a group of science teachers, I chose a Mathlet illustrating some rather basic mathematical concepts. Here's a slide capturing my objectives in showing you this recording. These are the same as my objectives were in the original presentation. The lecture fragment objectives were: the participant will be able to use Mathlets to support lecture-based instruction, to increase student participation in the lecture, to use the Mathlets to give students a visual correlate for symbols and calculations. I'm going to look at graph features. So I think graphs of functions are common language in science, and so I'm going to ask everybody to play along with this rather more simple tool that's written for a calculus course. So what you see is a graph. It's a graph of a third-order polynomial. The polynomial is described here. It's x cubed minus and so on. And these coefficients, 1, minus 2, 0.5, and 1, they're controlled by these 4 sliders. So a is the coefficient of x cubed, and b is the coefficient of x squared, minus 2. It's set at minus 2 right now. Part of the purpose of this tool is to help students get the idea of functions, and so by moving this slider here, I can change the value of x, and the student can see the output of the function and get the idea that a function is a rule that takes an input and produces an output. But after a while, you get more interested in the sort of global features of this function, and then that evaluation utility becomes kind of annoying, and I'm just going to set x equal to 0 now and look at the rest of what we see. So there are other features that students should be learning about, right, in a pre-calculus course. They may be interested, you may be interested in showing them where the function is rising or where it's falling. Little section there where it's falling in green, and you can see again the color coding happens. So rising and falling are simple things. Students have a harder time with concepts like concave and convex. Let's see, concave has to do with a cave, so it curves down like this. But it includes places where the function is increasing and decreasing. It has nothing to do with the issue of increasing and decreasing. This is a hard thing for students to get sometimes. And there's the convex portion. Well, right now, this function zooms up as x gets to be large. How would I change the coefficients to make it zoom down when x gets to be large instead?
The first coefficient is negative.
All right, so the first coefficient is this a. It's set at 1 right now. Let's experiment. There's a proposal from the floor. Let's find out. We can do an experiment here and see what happens. Very interesting. I'm not sure you've ever really visualized what happens when you start changing these coefficients. Well, it disappears off the screen. Now it's become negative. Ah!
Yay.
And there we go. Now it's coming down from plus infinity to the left and then sinking down to minus infinity on the right. So that leading coefficient is what determines that particular feature. Now look, we could continue to play with complicated functions like cubics, but let's go in the other direction and simplify this a whole lot. I'm going to set a to be equal to 0, so I've gotten rid of the cubic term, and actually it disappears in the display down here. And just for a start, I'm going to get rid of the quadratic term as well. So now this is just a first-order linear, if you like, first-order polynomial equation whose graph is a straight line, of course, and these two parameters are called the slope. There it is. I'm changing the slope and the intercept, and I can move the intercept up and down. So, you know, this is helpful for students, and maybe I can make it brighter by saying that it's rising. Well, so let's make it a little more complicated now. I'm going to reintroduce the quadratic term here, and there we go. So now I have a parabola, right? The graph of a quadratic equation is a parabola. So I have some questions about this parabola. The parabola doesn't seem to go through 0 right now. How can I make the value of this function, how can I make the graph go through the origin?
D, change the D. Translate down.
Okay. Okay, so if I set x equal to 0, then what's left is the constant term. So I guess I set d. I can move d. D just slides the graph up and down. Ha. All right, so I'll set d to be 0, and there we go. Now the graph goes through the origin. Now, how about this b coefficient? So I have a question for you here. So what will happen if I increase that b, the coefficient of x squared, in that formula? Will the graph, will the parabola get thinner, or will it move without changing its shape, or will it get fatter? I mean, increasing b, will it make the parabola fatter?
Thinner.
Should we take a vote? How many say thinner?
Thinner.
How many say fatter? See, now I saw some virtual votes there. This is one of the great reasons for not using public voting, but using private voting. And in a big lecture hall, I wish I brought them in, I use, I call them flashcards. I use numbered cards that have numbers like 1 through 8 on them. And the students will vote by putting up these numbers. And it's fantastic because I teach in a big lecture hall. I teach this course in a big lecture hall, and I see these numbers in the hall, and the students do not. The students do not look around to see how other people are voting. They respect the privacy of their peers. And it's a very genuine, you get a big scatter if you've asked a good question. You get a big scatter of different answers, which then leads to discussion as well. All right, well, so we didn't get, so I think the winner here in the election was, thinner?
Yes.
Thinner. If I increase B, it's supposed to get thinner. There we go. All right. And of course, if I make B negative, then I get a parabola that opens down. All right, so let's put B up to some positive number. Now, here's, and I'm going to make D look more interesting as well. All right, so now I have another question for you. What role does the coefficient of the linear term play? If I change that linear coefficient, which is 0 right now, if I increase it, what will happen to the parabola? So again, I'm going to come back to my...
It follows, the vertex follows our own shape.
So here's my question. C is the coefficient of the linear term, that x. So the parabola I'm looking at has the formula y is bx squared plus cx plus d. If I increase c, what will happen to the parabola? Now this is a pretty tough question.
It is. It goes left, like go. I don't know.
So this is the kind of question that really calls for, I mean, this would be an unfair question, I think, to a class. Because unless you want them to sit down and do a calculation, which I could ask you to do right now. But I tell you what, I'll do it with you, okay? And then we could take a vote now, but I don't think it's really fair because you have to do a calculation really to come up with an answer. So let's go back to the slide here. So what really is at issue is we want to know how this vertex moves. Let's find out how that vertex moves. Let's find out the x-coordinate of that vertex. So here's a calculation of the x-coordinate of that vertex. So I'm going to call x of v, the horizontal, the x-coordinate of the bottom of the parabola, right? And you can find that by setting the derivative equal to 0, or you can just do it with algebra, and that's called completing the square. So if I complete the square, that's this algebraic construction that gets rid of the middle term and writes it inside of the square of something. And if you think about it, it's got to have this form, x plus c over 2b is the right thing to put there. Because when you FOIL it out, it comes out with a cx in the middle. So all right, now where does the vertex occur? Well, it's going to occur when this term is 0. Right? That's when the minimum happens, when this term is 0. That means that x of v is minus c over 2b. Minus c over 2b, that's a really interesting formula. So it says a lot. If we have b fixed and we move c, I said increase c, what's going to happen to x of v? It's going to decrease, it's going to move left. Somebody said move left, and I think they knew something here. So let's go back to the screen and see what happens if I increase c. What's going to happen to the prediction is it's going to move to the left. So I'll move c to the right, and the prediction is the vertex is going to move left. Yay!
Yay.
Look at that. All right, so that's because it's a minus c over 2b, right? Now let's go back to that formula again, though. So there's c over 2b. That b, the coefficient of the x squared, comes into this formula too. And this says that the vertex should move a lot more if b is small, right? If the denominator is small there, then x of v will change more when I change c. Let's test that out. So I'm going to make b smaller. That'll make the parabola fatter, right? Yeah, okay. And now I'm going to change c, and the prediction is it's going to move much more. And it does. It moves much more dramatically. In fact, yeah, it moves much more dramatically because there's that b in the denominator for the formula. In fact, watch this. Watch what happens to that vertex when so here's b. I'm going to really play with b. I'm going to send b through 0. So then I get a straight line. There's no vertex. That vertex is going down to the left. It's going to go through infinity, out the other side, and come back on the other side. See that? It goes right through infinity and comes back on the other side. So now that was quite a bit of. So now look, this is polynomial. This is parabolas, right? I don't think I could have interested you, even in as much as I did, in the behavior of parabolas without the assistance of this kind of technology. The graphic nature of it is a big help in getting people's attention and letting them think about it. And this calculation I did, this is a fair bit of algebra. There's no numbers in here except for 2. This is all symbols. But because you can see the way they correlate with things on the screen here, the meaning of those numbers, those letters, the meaning of those letters is more transparent than if you're just giving an abstract lecture. So it's that combination of seeing things visually and then doing an analysis. It's a very powerful combination. What did you think about that lecture fragment? Once again, I began slowly, introducing the various features visible on the screen one by one. This Mathlet is considerably simpler than the first lecture fragment, so the exploration completed more quickly. Here are some questions for you to think about. This was an interactive lecture with quite a few suggestions and answers from the audience. How many students do you think provided that feedback? Do you think I had any information about how much the other students were understanding? Second question, what further lessons could you draw from this Mathlet in a lecture setting? Please refer to the course website for a written discussion of the lecture fragment that we have just seen. This is a good place for me to stress the following point. You must practice your use of the Mathlet in lecture. Decide in advance exactly what you want to do with it, which parts you want to call attention to and in what order, what sliders you want to move, and to what settings, and how you want to mix the Mathlet demonstration with chalk or projector content. Remember, things that interest you and seem obvious to you on the screen may not attract the interest of students or seem at all obvious to them. The Mathlets support a variety of active learning methods in lecture. For example, one can design concept quizzes around them. This methodology was systematized in physics education by Harvard physicist Eric Mazur. The idea is that one can interrupt a lecture with questions which all the students are really expected to answer. The key element of this method is to force each student to declare his or her belief about the answer to some conceptual question. If they're right, they're rewarded by having their belief confirmed. If they're wrong, they have to admit to themselves that they have been harboring a misapprehension, and this is the first step in learning. A well-constructed concept quiz results in a diversity of answers by students because it surfaces a variety of common misunderstandings. When this happens, you have to grasp the opportunity to let the students try to persuade each other of the correctness of their answer. This is peer instruction. It's also important to wrap up each such episode with a confirmation of the correct answer. In many classrooms in the United States, students answer these concept quizzes using clickers, which are handheld infrared or radio frequency communicators. I prefer to use a simpler technology, which I call flashcards. Each student is given a pack of 8 quarter pages with large numbers, 1 through 8, printed on them. They hold up the number labeling what they believe to be the correct answer. This is a surprisingly private form of communication. I see all the responses, but the students respect the privacy of their peers. The privacy afforded by flashcards or clicker technology really is important. Misapprehensions can be brought to the surface and addressed only in a safe environment. This module illustrates other strengths of the Mathlet technology. It can break up a lecture into bite-sized chunks. And the graphical and artistic nature of the Mathlets can excite interest in your students. Now, Please see the course website for exercises in using the Mathlets in lecture.